All right, let's go ahead and get started. A couple of things. Number one, just want to remind you, as we're deep in the heart of series about the peer assistant learning, also known as SI supplement instruction for Calculus 2, every Monday from 2 to 3 in Macy 201, every Tuesday from 11:30 to 12:30 in Fretwell 120, Wednesday again from 4 to 5 in Macy 201, and Thursday from 11:30 to 12:30 in Fretwell 120. So if you guys need some help with this stuff, here's another great avenue for you guys to go get some help. Things you have memorized thus far: name series. You have got the name series of geometric, telescoping, harmonic, and the P series. The tests you are up to are, number one, the divergence test, number two, integral test, number three, the direct comparison test, number four, the limit comparison test, and the one we were working on the last was the number five, the alternating series test. And what we were doing was the alternating series estimation theorem. So just to remind you guys what the alternating series estimation theorem is, that is, if you got yourself an alternating series, and we know from the alternating series test that if you got an alternating series where the terms decrease, go down, and the limit goes to 0, then the remainder for the alternating series, which is after you basically sum it up to a certain point, the remainder after n terms is equal to the true sum minus the partial sum Sn, which will always be less than or equal to Bn plus 1, the next term up. You get a bound on your error. So we did a bunch of problems last time. So I wanted to pick it up with this problem number 6 here. It says this: you got the sum as n goes from 1 to infinity of -1 to the n plus 1 divided by n factorial. So this is clearly an alternating series, the big old -1 to the n plus 1. It says determine whether the series is convergent or divergent. Well, being an alternating series, we should use the alternating series test. So as your series is the sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n factorial. The Bn part, the part without the alternating, the sequence part of your series without the alternation, is the 1 over n factorial. To check to see if an alternating series is going to converge or diverge, you got to check two things. The first thing you need to check is you got to write out some terms. This thing starts at 1. So n equals 1, n equals 2, n equals 3, ... You want to make sure the terms decrease. 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, ... Now 1 factorial is 1, so 1 over 1 is 1. 2 factorial is 2 times 1, which is 2, so that's 1/2. 3 factorial is 3 times 2 times 1, which is 6. That gives 1/6, ... Yep, my terms are decreasing. And the second thing you need to check is the limit as n approaches infinity of the Bn. This will be the limit as n approaches infinity of 1 over n factorial. So replace your n with infinity. I get 1 over infinity factorial. Well, let's think about it. What is infinity factorial? That's infinity times infinity minus 1 times infinity minus 2, that's infinity minus 3, ... That's like infinity on steroids. It's like huge. So this is 1 over really big infinity. And 1 over really big infinity is 0. So the limit goes to 0. Therefore, the sum as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n factorial is convergent by the alternating series test. So there's my statement and a proof of why this thing is convergent. Now, you're supposed to find the partial sum of S4. To remind ourselves, S4 is the sum of the first 4 terms. N equals 1, n equals 2, n equals 3, and n equals 4. I stop at 4. So plugging this into my series, 1 plus 1 is 2. -1 squared is 1 times 1 over 1 factorial. Plus plug in 2. 2 plus 1 is 3. -1 cubed is back to -1 over 2 factorial. Plus 3 plus 1 is 4. -1 to the 4th is 1 over 3 factorial. plus 4 plus 1 is 5. Negative 1 to the 5th is negative 1 over 4 factorial. So if I clean this up, 1 over 1 factorial is 1, plus a negative is minus. 1 over 2 factorial is 2 times 1, which is 2, plus 1 over 3 factorial. 3 times 2 times 1, well, that's 6. That's 1 6. Minus 1 over 4 factorial. 4 factorial is 4 times 3 times 2 times 1, 24. And I stop there, and I grab my handy-dandy calculator, and because they want to just S4, so it's the sum of the first 4 terms. So putting this on my calculator, this will be 1 minus a half plus a sixth minus a 24th, and I end up getting 0.625. Does that make sense? This is what S4 is, your partial sum 0.625. Sum of the first 4 terms. Now, you're supposed to find R4, a bound for R4. Remember, it's an error. So absolute value of R4, which is truly equal to the true sum, which I actually don't know what this thing actually adds up to be, minus the partial sum S4, will be less than or equal to, it's supposed to be Bn plus 1, but here n equals 4. So 4 plus 1 is 5, B5. Remember, your Bn is the part of is the sequence part of your series without the alternation, which is 1 over n factorial. So if I want B5, this would be 1 over 5 factorial. And what's 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. So this is 1 over 120. So an error for the R4, which is the remainder part of your S4 partial sum, will be less than or equal to 1 over 120. Now, the question is, of course, how many n's, how many terms do we need to take it out to for Rn to be accurate, to be within 0.0001? Now, we did a couple of these problems last time, but just to remind you, Rn, which is equal to the true sum minus the partial sum, is less than or equal to Bn plus 1. Now, Bn in this problem is the sequence part of your series without the alternation, 1 over n factorial. Okay? So, Bn plus 1 B sub n plus 1 would be 1 over n plus 1 factorial. Now, we want this error to be within, be less or equal to 0.0001. So this is 1 over n plus 1 factorial, and that's got to be less than or equal to 0.0001. And your mission here is to solve for n. Now, I did a problem before where we had just a regular n in the bottom, and you cross multiply and you divide it, then you had to round up. It wasn't too bad. I even did a problem where the n was in the exponent. You had to use logarithms to solve for that. This problem, I want you to solve for n. It's embedded inside of a factorial. How do you do that? Well, guess and check, because there's no real way to solve for a factorial. There's no anti-factorial button that you get rid of the factorial so you can solve for n on. So basically, you just have to start and testing here. So we're going to start with, like, for example, n equals 4. I just picked 4 because 4 is what we had up here. So n equals 4. Now I'm going to put it on the calculator and let's see what the error is. So 1 over basically 4 plus 1 factorial. That's 1 over 5 factorial, but I'm going to type it in just like this. 1 divided by parentheses 4 plus 1. And your factorial button is located under the math button. Go to math, scroll over to probability, PRB, and it's number 4, your factorial button. You could type in 5 times 4 times 3 times 2 times 1. Then you get up getting 0.0083333. 0.0083333. Is that less than 0.0001? No. Not my guy. Well, then let's try n equals 5. This will give you 1 over 5 plus 1 factorial. which is going to be, and I'm going to sit there and pull this guy down, and second entry. This is that guess and check. With factorials, you don't have much of a choice. I got 0.00138. 0.00138. Is that less than or equal to 0.0001? No, it's not. It's 0.001. This is 0.0001. So not going to be that guy. So let's try the next guy. N equals 6. This will be 1 over 6 plus 1 factorial. And that's going to be, recall this thing back down, 1 over 6 plus 1, which is 7. 1 over 7 factorial is, what is this guy? 1.984 e negative 4. What does that e negative 4 stand for, you? Times 10 to the negative 4th, which means I move this decimal 4 places to the left. That'll be 0.0001984. Is 0.0001984 less than or equal to 0.0001? No, it's not. It's darn close, but not quite. So no. So let's try probably my answer here. N equals 7. This will be 1 over 7 plus 1 factorial, which would be 1 divided by 7 plus 1 is 8 factorial, but I'm just going to type it in 1 over 7 plus 1 factorial. And I get 2.48 e negative 5. So move my decimal place 5 places to the left. That'll be 0.0000248. Is 0.0000248 less than or equal to 0.0001? Yes, it is. So the answer to this problem is you need to just calculate 7 terms, get S as 7, and that will give you your tolerance of your series to be within 0.0001. Again, if you go back and look at the problems that we did before very quickly, the first problem we did with this stuff, when we're trying to find n to be this kind of tolerance, this was just 1 over n, so your bn was 1 over n, so bn plus 1. This was a straight, easy cross multiply and divide and solve for n type thing here. The one that was a little more painful was when we had a geometric series, and I wanted to use my alternating series estimation error bound formula for this. And so I end up getting 2 over 3 to the n plus 1 less than or equal to 0.001. And I had to manipulate it and then use logs on both sides and be able to solve. And then I had to do some rounding. So regardless, I had to round up to 5.9. So you end up getting 6. With this one, there's no solving for n in the traditional sense. It's more guess and check. Keep plugging in numbers until you actually get one that actually satisfies the equation. All right. Definition. A series is absolutely convergent. Absolutely convergent is what we're basically talking about. So, when we're going to be looking at an alternating series, when we focus on an alternating series, we're going to rank it 1 of 3 different ways. Something called absolutely convergent, or it can be called conditional convergent, or it's going to be called a divergent series. So you've got 3 different options here. Now, definition of an absolute convergent series is this. If you take the sum as n goes from 1 to infinity of the absolute value of an, and if that thing is convergent, then the original alternating series, the sum as n goes from 1 to infinity of negative 1 to the n, is called absolute convergent. Let me try to speak to you guys in English on this. We're going to look at a series and we're going to declare it to be absolute convergent, which means when you take the absolute value of an alternating series, what happens to the negative 1 to the n's? What happens to all your little minuses when you take the absolute value of it? They become plus. So your alternating part actually goes away. Drop the alternating and look at it as a series. And if that series converges, then the original alternating series is going to be called absolute convergent. So absolute convergence is what we call your strong convergence from an alternating series perspective. Because it didn't matter if it was alternating or not. The darn thing would have converged anyway. That's absolute convergent. Drop the negative 1 to the n, look at that series, and if that series is convergent, then it's absolute convergent. But when you take the absolute value of this guy and it doesn't converge, it's divergent, then you got one more choice. Basically, you got to check for conditional convergent. A series is conditional convergent is when you go back and put the negative 1 to the n and use the alternating series test on them, and it converges. That meant that the series had to have the negative 1 to the n mass on it to actually have a chance of converging. So since it does it, it's going to be convergent, but it's called conditional convergent. And last thing, if it fails conditional convergent, if it fails converging by the alternating series test, you only got one other option. If it doesn't converge by the alternating series test as an alternating series, it must do one last thing. It must diverge. So this is basically your hierarchy. Absolute convergent is your top of any kind of alternating series. Then conditional convergent, that meant you had to have that negative 1 to the n. Otherwise, the darn thing's going to diverge. So we're going to rank absolute convergence here. So that's what I'm kind of referring to in this little kind of flow chart type thing that we discussed up here. So let's take a look here. Let's take a look at this series right here. This is the sum as n goes from 1 to infinity of negative 1 to the n plus 1 over n cubed. It's in the directions. Listen to me. The directions tell you this. Here's an alternating series. Is the alternating series absolute convergent, conditional convergent, or diverges? You got to rank it. Is it A, B, or C? Absolute convergent, conditional convergent, or diverges? I think Weber calls it A, C, or D. Absolute convergent, conditional convergent, or diverges for proper letter terms. But here we go. First thing you're going to check, when you get an alternating series with those directions, the first thing you're going to check is absolute convergence. Check your strong stuff first. For absolute convergence, you take your series. The sum as n goes from 1 to infinity, and you throw absolute values around the sequence part. Absolute value of negative 1 to the n plus 1 over n cubed. And clean it up. Now, what's the absolute value of the negative 1 to the n stuff? Absolute value of a negative is always what? Positive. And 1 to any power is 1, so absolute value is going to kill off this negative 1 to the n plus 1 stuff. So this turns into the sum as n goes from 1 to infinity of 1 over n cubed. Now, either use a test, or if you happen to know this is a name series, give me the name and tell me all about it. But now analyze this guy. What is this sum as n goes from 1 to infinity of 1 over n cubed? It's P series. Tell me about it. P equals what? 3, which is bigger than 1, which means it does what? It converges. So when I took the absolute value of my alternating series and I created a series that converges, therefore, 3 dots in a triangular fashion, therefore, the original alternating series, the sum as n goes from 1 to infinity of negative 1 to the n plus 1 over n cubed is absolute convergent. Because whether you had negative 1 to the n, or in this case n plus 1 with it or not, the darn thing would have converged anyway. That's called absolute convergent. Okay? Here's the deal. When you got an alternating series that is not absolute convergent, then you're going to check conditional convergence by the alternating series test. Take a look at the next guy. Here's a series. It's the sum as n goes from 1 to infinity of negative 1 to the n divided by n. And again, it's in the directions. I'm telling you the directions right now. The directions on these examples are, here is an alternating series. Is it absolute convergent, conditional convergent, or does it diverge? Those are my directions. I'm not just saying this thing converges or diverges. If I had that question, I'd just use the alternating series test on the darn thing and tell me, because it'll tell me what's going on. But they put the words, is it absolute convergent, conditional convergent, or does it diverge? So you do it in order. I'm going to check for absolute convergence first. Absolute convergent, question mark. I'm going to take my series, the sum as n goes from 1 to infinity. I'm going to take the absolute value of the negative 1 to the n over n. And I clean that up. That's the sum as n goes from 1 to infinity. Absolute value of this negative 1 to the n makes it 1 to the n, which is just 1. It completely drops off the negative 1 to the n stuff. Over n still stays. What kind of series does this do? This is the harmonic series. And what does the harmonic series do? Diverges. Which means it is not absolute convergent. Does that make sense? It has failed being absolute convergence. Then you go to level 2. Is it conditional convergent? Conditional convergent, question mark. You go back and take your series and put the alternating part back on there. Negative 1 to the n over n. And then check the alternating series test. Putting the negative 1 to the n, now it's an alternating series. Is this thing going to converge or diverge by this? Well, for alternating series test, your Bn, the part without the alternation, is the 1 over n. You got to check two things. Number one, does the terms go down? This series starts at 1, so n equals 1, n equals 2, n equals 3. Got to show me 1 over 1 is 1, 1 over 2, 1 over 3. What's happening to my numbers? They're decreasing. And number 2, you take the limit as n approaches infinity of the 1 over n. 1 over infinity is 0. The terms go down and the limit goes to 0. What does that tell you? That this series is convergent by the alternating series test. So we therefore, in terms of the original problem, by the alternating series test, the alternating series is convergent. We would say that the sum as n goes from 1 to infinity of negative 1 to the n over n is conditional convergent. And we call it conditional convergent, there you go, conditional convergent because you had to have the condition that the negative 1 to the n was on the problem. Does that make sense? So it does, this series is convergent, but we would call it conditional convergent. One last thing. If this series actually was divergent, the limit didn't go to 0 or something or other, then you're done. It's called diverging. So this is really the last test, because if it fails being conditional convergent, you only got one other option. The series is divergent. So you're putting these things in order. All right. What test number are we up to? Number 6. Here is your test number 6. It is called the ratio test. The ratio test says this. For the sum as n goes from 1 to infinity of an, a general or alternating series, if the limit as n approaches infinity of the absolute value of an plus 1 over an equals L. And this L value is less than 1. This means that the series is going to be convergent, and it's absolutely convergent if it's alternating series. If L value is greater than 1, then the series is going to diverge. And if L happens to equal to 1, the test was inconclusive. You got to try another test. All right, so this one is the big test here. This is the test you're going to use for the really hard series. You got a hard series. It may be alternating or a regular series. Okay? And what you're going to do here is you're going to look at the an part and replace the n with n plus 1 and put it in the top as a sequence, and put in the denominator an, just copy it down and clean this stuff up, and then take the limit as n approaches infinity. You're going to get a number, L. If this L number is bigger than 1, then the series is going to diverge. If the L is less than 1, the series is going to converge. And if it was an alternating series, because you are using absolute values, we would say this is absolute convergent. But if it's not alternating, you just call them convergent. You don't say absolute convergent for a non-alternating series. It's got to be an alternating series to be an absolute convergent series. Otherwise, it's just called convergent. And if L equals 1, you did all this work and wasted your time. You should try another test. Now, honestly, when L equals 1, you should be ashamed of yourself. It's probably some real simple series, and you tried to use this particular test, this very large test, to prove something that's very, very simple. You know, it's a P series, P equals 3 or some crap like that, that you should have just looked at and went, oh, wow, this is an easy test. But if you use the ratio test on it. So I try to come up with stuff to try to make people remember this mess. All right, so this is the deal. The ratio test, for all my military fans out there, and all the folks that we're in the military and stuff, understand this better than anybody. This is your nuclear bomb of tests. This is the big guy. When do you want to drop the bomb? It's got to be a real tough situation out there against you. Large problems here. You're going to use the ratio test on this big series. Powers of n and or factorials. If you got a nasty looking series that has powers of n and or factorials in it, then you want to drop the bomb on it, the ratio test. Okay? And that ratio test will tell you whether the series is going to be converging or diverging. Okay? But if, for example, you got a long little series out there in the middle of the field somewhere, one little soldier not doing much of anything, we got him spotted, we know where he's at, we know what he's doing. Do you want to waste all your time, effort, money, and expense and dropping a bomb on the entire continent to blow this guy out of the water, or do you want to use like another test? Because this is what happens. You're going to waste all your time, and L is going to be equal to 1. Waste all your time, energy, and for government, money on all this stuff, and it's actually inconclusive. You really didn't get anything out of it. Now, granted, this is government, so this is a possibility. But the fact of the matter is, you don't want to use it on the simple stuff. When do you want to use a ratio test? 2 major situations. Powers of n and or factorials. With other stuff, yeah, great, don't care about that. But you got to have a power of n or a factorial on it. That's when you're going to use your ratio test. Bomb that guy. Nuke him out of the world. This will tell you exactly what these hard series are going to do. Take a look at this first guy. This is the sum as n goes from 1 to infinity of 3 to the n divided by 4 times n factorial. What do you see in this problem? Powers of n and factorials. This is a choice guy for blowing him out of the water. The ratio test is designed for this hard integral. It's going to be the hard series. So, here we go. The an part is the sequence part of your series, which is 3 to the n over 4 n factorial. Okay? So, I'm going to do the ratio test. I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. This is equal to the limit as n approaches infinity of the absolute value of an plus 1. I'm going to replace all the n's with n plus 1. This will be 3 to the n plus 1 over 4 times n plus 1 factorial. That is what n plus 1 looks like. Divided by an. You just copy it. 3 to the n over 4 times n factorial. Now, you got to clean this guy up. And here's the trick right here that I'm going to save you guys lots of time and effort. When you have a fraction divided by a fraction, what do? Invert, multiply, flip, and multiply. But while you're flipping and multiplying, go ahead and group together like terms. That's going to save you like buku-doodles of algebra time in cleaning this thing up. Flip and multiply and group together like terms. So this will be equal to the limit as n approaches infinity of the absolute value of, your fraction is really the numerator. It's 3 to the n plus 1 divided by 4 times n plus 1 factorial. All that's in the denominator. So when I take the fraction in the denominator and flip it up, the 4 shows up on top, the n factorial shows up on top, and the 3 to the n shows up on bottom. And I went ahead and grouped together like terms because it saves me lots of algebra time. Because the goal of the ratio test is somebody's going to cancel. What cancels here? Let's take a look at this. First one's real obvious. What cancels? The 4's cancel. Now let's take a look at this guy here. 3 to the n plus 1 divided by 3 to the n. 3 to the n plus 1 by definition is 3 times 3 to the n. I just pulled off one of those guys, so now the 3 to the n on top and the 3 to the n on the bottom are going to cancel. It does leave me with a 3 left over. Now, what about the other part? N factorial. What is the definition of n factorial? The definition of n factorial is n times n minus 1 dot 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 all the way down to 1. What is the definition of n plus 1 factorial? It is n plus 1 times n minus 1 all the way down to 1. Factorials are going to cancel. N factorial is n times n minus 1 all the way down to 1. N plus 1 factorial is n plus 1 times n minus 1 all the way down to 1. The n's cancel, the n minus 1's cancel, the dots cancel, and the 1 cancels. You're left with an n plus 1 in the denominator. So, when you clean this up, this will be the limit as n approaches infinity of the absolute value of 3 on top and divided by, what's left on bottom? N plus 1. Everybody else canceled out. Now, take your limit as n approaches infinity. When you plug in infinity, you get 3 over infinity plus 1, which is infinity. What's 3 divided by infinity? 0. In this problem, L equals 0. Now let's apply the ratio test. My L, which is equal to 0, is what? Is it, quote, less than 1, greater than 1, or equal to 1? It's less than 1. Therefore, this series, the sum as n goes from 1 to infinity of 3 to the n over 4 n factorial is what, according to the ratio test? It's convergent. We don't use the word absolutely convergent because it wasn't an alternating series to begin with. We only use the word absolutely convergent if it was an alternating series. We would just say is convergent by the ratio test. Does that make sense? It's convergent. This is a convergent series. Now, the directions tell me to do this. Here's a lone little soldier, just sitting there, not bothering anybody. We got him targeted. We know what the sum of n goes from 1 to infinity of 1 over n cubed is. What's this dude's name? P series. What's P equal to? 3 is less than 1. What's it going to do? Converge. You're done. But no, we're the government, and we got to find out if this bomb really works or not. So let's nuke it. So we're going to use the ratio test on this thing because I want to show you what happens when you use this nuclear bomb of test on a lone little soldier sitting out in the middle of the field and what exactly happens. So I've been told to use the ratio test. Now WebWork is going to tell you the same thing as well. So when you see a problem that you actually know what it is, and it's a simple P series or something like that, it's not a power of n, it's not a factorial. You really shouldn't use the ratio test because it's not going to do a darn thing for you, but I'm going to show you the math anyway. Here we go. I've been told to use the ratio test, so I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. An is 1 over n cubed. 1 over n cubed. What would an plus 1 be? That would be 1 over n plus 1 cubed. Does that make sense? Just replace n with n plus 1. So I'm going to plug it into this guy. This will be the limit as n approaches infinity of the absolute value of 1 over an plus 1 is n plus 1 cubed divided by 1 over divided by an, which is 1 over n cubed. Now, clean this guy up. I'm going to invert and multiply. And there's no alternating on this stuff, so these absolute values are absolutely useless here. I'm going to flip it up and multiply. This will be n cubed divided by n plus 1 cubed. And I dropped the absolute value because nothing's negative in this thing. Does that make sense? Now, show you some algebra anyway. They're both got the same powers. It's n cubed divided by n plus 1 cubed. You can factor out your cube. So this will be equal to the limit as n approaches infinity of n divided by n plus 1 cubed. Because I'm using limit properties. Remember, you take the limit as n approaches infinity of where the n's are. Now that I factored out the cube, all the n's are in the inside. According to my limit properties from Calculus 1, this is equal to the limit as n approaches infinity of n over n plus 1 quantity cubed. Now, take the limit as n approaches infinity of n over n plus 1. What do you get? 1. Degree of the top equals degree of the bottom. You could L'Hopital rule it if you want to. It's your choice, but it's going to be 1. And you're cubing it, so what do you get? 1. Bum, ba, dum, ba, bum. Therefore, the L factor from the ratio test equals 1. What does that tell you? Inconclusive. You should try another test. Why don't you say ratio test is inconclusive? Big old question mark there. However, what was this dude's name? The sum as n goes from 1 to infinity of 1 over n cubed is a P series. P equals 3, which is greater than 1, is convergent. Does that make sense? It's a convergent P series, but we've been ordered, dropped the bomb, we wasted all that time and energy, and what do we end up getting? L equals 1, which the ratio test says is inconclusive. Try another test. Why don't you just look at it and tell me it's a P series and we win the game? Does that make sense? Don't do the ratio test unless you're told to. The only time you ever use a ratio test is powers of n and or factorials. This had no power of n. This did not have a factorial. You shouldn't be using ratio test on this guy. Here's one. This is the sum as n goes from 1 to infinity of negative 3 to the n divided by n cubed. Now, this guy is an alternating series. Yes, it's negative 3 quantity to the n, but you can factor off negative 3 is negative 1 times 3 raised to the n, which makes it the same thing as negative 1 to the n times 3 to the n over n cubed. This is the same thing. Just wanted to show you that it really is an alternating series. So if this thing is convergent, well, first off, notice we do have a power of n. So here is a great time to use the ratio test. I mean, it's 3 to the n, not -1 to the n. -1 just makes it alternating. We've got to have a number to an n. Powers of n, doesn't have any factorials in it, but that's okay. Powers of n or factorials. This is a ratio test problem. Ratio test will actually do this guy here. So, here we go. I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. This will be equal to, and I'm going to use my cleaned up version here, the absolute value of, limit as n approaches infinity, of the absolute value of -1 to the n plus 1, 3 to the n plus 1, divided by n plus 1 cubed, replacing all the n's with n plus 1s, divided by an. An is you just recopy it. This will be -1 to the n times 3 to the n divided by n cubed. Just want you to see the an plus 1 divided by an as you're doing your algebra. Now, take the limit as n approaches infinity, invert, multiply, and group together like terms. This will be equal to the limit as n approaches infinity of the absolute value of, this will be -1 to the n plus 1 times 3 to the n plus 1 divided by n plus 1 cubed. When I invert and multiply, the 3 to the n shows up on top. I'm grouping them together with the n plus 1 cubed. The 3 to the n will flip up, will be on the bottom. I'll group it with the 3 to the n plus 1. And the -1 to the n will actually be on the bottom. Now, I'm going to save myself lots of time here. What does an absolute value do to -1 to any power? Makes it what? Absolute value. Makes it positive. So pretty much you can cancel this stuff out because the absolute values are killing off the -1 to the n's or n plus 1s or whatever. Absolute value, they're not canceling. Well, yeah, one of them will cancel. We'll be left with a -1, but absolute value of that's still 1. They completely kill each other off. They're gone. But I got 3 to the n plus 1. I can pull one of these guys off. This will be 3 times 3 to the n, and the 3 to the n's cancel. You are left with a 3 on top, just to remind yourself. Over here, I'm going to factor out the power. So cleaning this up, this will be the limit as n approaches infinity of 3 times, here we go, it'll be n over n plus 1 cubed. I just left off the 3 and I'm focusing on factoring out the cubed. And now I'm going to put my limit as n approaches infinity with the n's. That goes inside my parentheses. So this will be equal to 3 times the limit as n approaches infinity of n over n plus 1, and that would be cubed. But we just did this a few seconds ago. What is the limit as n approaches infinity of n over n plus 1? 1. Degree of the top equals degree of the bottom. You can use L'Hopital's rule if you want to, but it's going to be the ratio of leading coefficients, which is 1. And 1 cubed is 1, so this will be 3 times 1 cubed, which is 1 cubed is 1 times 3 is 3. Your L equals 3. But according to the ratio test, if L is less than 1, the series is less than 1 is convergent. It'll be absolute convergent if it was an alternating series, which this is. If L is greater than 1, the series is divergent. If L equals 1, you should have tried another test. This was too simple. But we didn't get 1. What do we get? 3. And since 3 is bigger than 1, therefore this series, the sum as n goes from 1 to infinity of -3 to the n over n cubed is divergent. Greater than 1 is divergent. Does that make sense? Questions? All right. So, some general examples right here. Now, understand, here is my question. And this is going to be the question on the test. Well, this one I could give you a couple of different kind of questions here, but this is the one I'm going to give you. Here's a series. Is it converging, diverging, and state why? What test would you use? I didn't ask where it was absolute convergent. If it was absolute convergent, conditional convergent, or whatever, that's a different story. I would check the absolute value and do my little steps here. But I'm just asking you a straight question on these questions right here. Convergent or divergent, and prove it. What about this series? The sum as n goes from 1 to infinity of negative 1 to the n times n over n squared plus 1. What test would you use? Would you use a ratio test on this one? No, wasting your time and money and effort. Don't be the government. There's no power of n. There's no factorials on this thing. Why waste your time? But here's the thing. So I'm not going to use a ratio test on it. So look at it some more. Remember, I got lots of tests to choose from. What were the tests that I have memorized here? Oh, I got my little sheet of paper from first part of class here. So far, we got 6 tests now. We got divergence test, integral test, direct comparison test, limit comparison test, alternating series test, and now we have the ratio test. So there it is. Which one would I use on this one? Well, here's the clue. Negative 1 to the n stuck on this thing. So what test am I going to use since they gave me the question, convergent or divergent? I'm going to use the alternating series test. Let me make it really straightforward in your face. You know why I'm going to use the alternating series test? Because it's alternating. Don't make it too deep on this stuff. It's an alternating negative 1 to the n or cosine n pi. Makes the alternating series test. Unless they put the words absolute convergence, conditional convergence, I'm going to use the alternating series test. Now, if I've got alternating series with some powers of n and or factorials, I'm going to use the big nuclear bomb of test, the ratio test, and knock that sucker out because that's what I need to do. But this was pretty simple, and it's an alternating series. So I'm going to use the alternating series test here. All right? So the Bn is the part without the sequence part without the alternation, which would be the n over n squared plus 1. I'm going to check 2 things. Number 1, I'm going to write down some terms. N equals 1, n equals 2, n equals 3. Look for the pattern here. 1 over 1 squared is 1 plus 1 is 2. So when I plug in 1, I get 1 half. Plug in 2, I get 2 over 2 squared is 4 plus 1 is 5, so 2/5. Plug in 3, I get 3 over 3 squared is 9 plus 1 is 10, ... 1 half, 2/5, 3/10. That's 0.5, that's 0.4, 0.3. What's happening to my terms? They're decreasing. Big old check there. And number 2, when I take the limit as n approaches infinity of n over n squared plus 1, officially I'm going to get infinity over infinity. But so I'm going to show you the work on this on the L'Hopital rule it. This will be equal to the limit as n approaches infinity of derivative of n is 1, derivative of n squared plus 1 is 2n. Plugging in infinity, 1 over 2 times infinity is infinity, 1 over infinity is 0. So let me get this right. The terms decrease and the limit goes to 0. Therefore, what is this series? Sum as n goes from 1 to infinity of negative 1 to the n times n over n squared plus 1 is what? Convergent by the alternating series test. Does that make sense? Here's one. The sum as n goes from 1 to infinity of 10 to the n divided by n plus 1 times 4 to the 2n plus 1. Yeah, we made you nasty. What test you going to use on this one? What kind? Ratio test. Why? It's a nasty looking series. I got a bunch of other stuff chunked into it, but most important, I got, with some n's, numbers raised to powers of n. Numbers raised to power of n and or factorials, I'm going to use the ratio test. So this is a great example of ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. This will be equal to the limit as n approaches infinity of absolute value an plus 1 will be 10 to the n plus 1 divided by n plus 1 plus 1, I'll clean it up later, times 4 to the 2 times n plus 1 plus 1. We've made this so nasty because I want to show you what plugging in n plus 1 to n actually looks like. I replace all my n's in the actual series with n plus 1, divided by an, which is just 10 to the n over n plus 1 times 4 to the 2n plus 1. So this would be equal to, when I clean them up, the limit as n approaches infinity of. Now you take your numerator and stretch them out. Go ahead and clean them up. This would be 10 to the n plus 1. Divided by n plus 1 is actually n plus 2. And divided by 4 times. Here I'm going to distribute. That'll be 2n plus 2 plus 1 more is 2n plus 3 when you clean up the exponent there. Now flip and multiply, invert multiply. The n plus 1 shows up on top. The 4 to the 2n plus 1 shows up on top, and the 10 to the n will actually stay on bottom. So I'm doing a lot of algebra in this invert multiply group together like term stuff. Now, who cancels? Powers of n are going to cancel out here. I got 10 to the n plus 1 divided by 10 to the n. 10 to the n plus 1 is the same thing as 10 times 10 to the n. Pulled off one of my 10s, and the 10 to the n's cancel. 4 to the 2n plus 1 divided by 4 to the 2n plus 3. Which one has more, the top or bottom? Bottom one. How many more does the bottom one have than the top one? 2. I'm going to pull off the bottom one. I'm going to pull off 2. That'll be 4 squared times 4 to the 2n plus 1. Because remember, when you multiply, you have to add exponents. 2 plus 2n plus 1 is 2n plus 3. And the 2n plus 1 is 4 to the 2n plus 1's cancel. So you're left with the limit as n approaches infinity of 10 times n plus 1 divided by 4 squared, which is actually 16, times n plus 2. Now take your limit as n approaches infinity. What are you going to get? Well, you get the 10/16. You can pull out front. That'll be 10 over 16 times the limit as n approaches infinity of n plus 1 over n plus 2. What's the limit as n approaches infinity of n plus 1 over n plus 2? The degree of the top equals the degree of the bottom. You can L'Hopital it if you want to. What should you get? 1. So you're left with 10/16, but that just bothers real math people. 10/16, same thing as what? 5/8, and that is your L value. L equals 5/8. Now let's do the ratio test. Ratio test says this, things you've got to have memorized. When L is less than 1, the series is going to converge. And if it was an alternating series, it would have been absolute convergent. If L is greater than 1, the series is going to diverge, and L equals 1. Shame on you. You should have tried another test. So this is L equals 5/8, which is less than 1, which tells me that my series, the sum as n goes from 1 to infinity of 10 to the n divided by n plus 1 times 4 to the n plus 1 is what? Less than 1 is convergent. It's not an alternating series, so we don't use absolute convergent. Just convergent by the ratio test. Does that make sense? Questions? Now take a look at this next guy. On this one right here, I've got 2 options I can use. It's the sum as n goes from 1 to infinity of 3 to the n times 4 to the 1 minus n. What test would you use? I got 2 I could use. It is a series that has numbers raised to powers of n. So I could use the ratio test. And to answer the question, is the series converging or diverging? I could use a ratio test. Or what other test I could use? It's not just a test, it's actually the type of series it is. What is that? Or I could use the geometric series. Because it is a geometric series, so I actually don't have to test it. I actually know what this thing is going to do. I can tell you exactly what it converges to. Does that make sense? What I'm trying to show you is, hey, there's more than one test, more than one way you can get an answer on this stuff. Okay? Which test would you like to use? You want to use a ratio test or geometric series? Geometric series. It'll be easier because of this. So I'm going to use the geometric series because the ratio test is a lot of time and effort to show me how much algebra I had to do there. This one, that 4 to the 1 minus n, I can put it on the denominator, and it becomes the sum as n goes from 1 to infinity of 3 to the n divided by 4 to the negative 1 minus n. This is for your benefit. Because when I put something in the denominator that was originally in the numerator, I got to make the exponent negative. I'm going to distribute. So this will be the sum as n goes from 1 to infinity of 3 to the n divided by 4 to the distributing. That'll be n minus 1. And what we have remembered from the geometric series, the sum as n goes from 1 to infinity of a r to the n minus 1. It converges to a over 1 minus r if the absolute value of r is less than 1. And it diverges if the absolute value of r is greater than or equal to 1. Things we have memorized. So I want to have that n minus 1 power. The 3, I got 3 to the n. I want n minus 1 power. I'm going to pull off one of those guys. So this is sum as n goes from 1 to infinity of 3 times 3 to the n minus 1 over 4 to the n minus 1. Because they have both the same power of n minus 1, I'm going to factor it out. That'll be the sum as n goes from 1 to infinity of 3 times 3/4 to the n minus 1. That tells me A equals 3, R equals 3/4. Absolute value of R equals absolute value of 3/4 with 3/4 less than 1, which means this thing is converging. This is a convergent geometric series. You want to tell what it converges to? Sure. The geometric series converges to A over 1 minus R. A is 3 over 1 minus 3/4. That'll be 3 over 1 minus 3/4 is what? 1/4. We invert multiply, that'll be 3 times 4. It actually adds up to be 12. Does that make sense? I could have used the ratio test on this one, and it would have told me that the L was like 0, and it would have been less than 1, or L equals 3/4 something. It'll be less than 1, which means it would have converged. But the geometric series itself told me what it actually converges to. So if you notice it's a geometric series, you know exactly what it converges to. So study hard on this stuff. We got one more test, and we'll finish this out last time. It's a very specialized test. Test number 7 is called the root test, and we'll do that one next time. See you guys then.